So, today's lesson, I just want to kind of recap, summarize about electric field strength. And before I recap about electric field strength, let's quickly talk about electric fields, shall we? If you have a charged object, say it's like a tennis ball that has electrons scuffed off of it, so it's lacking electrons, it's missing electrons. It has an overall positive charge. Yes? Well, if an object has an overall charge on it, the space around the object, this space all around it, like this, is altered. It's no longer the same. Even if it's empty space, something is different about it. If you put your hand in this empty space, the hairs on your arms would start to stand up. Something is different about it. Physicists say that this something different is an electric force field. It's invisible. It can only be detected when another charged object is placed in that field, but nonetheless, there's something very different in that space. So electric field mapping is a way to visualize this invisible electric field space. So how is it done? You pretend to place a tiny imaginary, free to move positive charge in the area around this charge. Whether this charge is positive or negative, by agreement, everyone agrees to pretend to push a tiny imaginary positive charge right there. I personally call it a tipsy. Whoa, for short. Tiny imaginary positive charge. Get it? Tipsy. Tiny imaginary positive charge. Yes. If you put this tiny imaginary free to move positive charge right there, and then you draw an arrow how it would respond to the main charge that's creating the invisible force field, how would this little tiny imaginary free to move positive charge move? Outward, okay? And now, normally we don't even draw the tiny imaginary free to move positive charge. We just pretend to place it there and ask ourselves, how would it move? Oh, it would move this way. If I put it here, it would move that way. If I put it here, it would move this way. If I put it here, it would move that way. If I put it here, it would move this way. It would move this way. Now we have a visualization of the invisible electric field. These arrows are called electric field lines, and electric field lines always show what a tiny imaginary positive charge would do. You see the spacing between the lines right here? The lines are relatively close, but if you move a little farther away, look at the spacing. This line now and this line, they're a little bit farther apart. So the spacing of the lines tells you how strong the field is. Here, the field is stronger because these lines are closer together. Here, the field is weaker because these lines are farther apart. The spacing tells you the strength of the field. Sometimes the object that produces the field isn't shown. For example, let's say I had a negative charge right here, yes? An object that has extra electrons. And then I went and mapped the invisible electric field around this negative charge. Well, if I pretend to put a tiny imaginary positive charge here, it would be attracted. If I put it here, it would be attracted. If I put it here, it would be attracted. Here, it would be attracted. Here, it would be attracted. So this is a way to represent the invisible electric field around that negative charge. The electric field lines always show what a positive charge would do. Now, sometimes the charge that creates the invisible electric field is not shown. For example, I can erase this now. Sometimes you're only shown the electric field itself. And you could be asked the question, shown the electric field in red, which point has the greatest field strength? Point A, point B, or point C? Paul?
A.
Point A, because the field lines are the closest there. Okay. Another question that could be asked, if a positive charge was placed in the electric field shown, in which direction would it experience the electric force? In direction 1, in direction 2, in direction 3, in direction 4. If a positive charge was placed in that red electric field shown, which way would it experience an electric force? Say it loud, say it proud, Mike. Choice 4. Yes? But now the next one's kind of tricky. Okay? If an electron or a negatively charged object was placed in the electric field shown, which way would that negative charge experience a force? 1, 2, 3, or 4? Yeah, the answer would be choice 2. Because what did the red line show? What a positive charge would do. So you got to remember that a negative charge would move in the opposite direction. You guys with me on that? So far all is well. We know the field is like strong here, a little bit weaker there, a little bit weaker there. We know that a proton would move this way, an electron would be forced the opposite way. But now what we want to do is we want to actually define how strong it is. It's not good enough to say, hey, it's strong there, weak, weaker. We want to be able to say it's like 57 units strong right there. We want to be able to give it a number, a measurement. So that's what comes next. Electric field strength. Let's say we're given a positively charged object. I always like to draw circles around the positive charge to remind me those positive charges are the protons. They're locked up in the nucleus. They're not free to move. And basically, let's say that this charge right here is positive 5.8 times 10 to the negative 6 coulombs. And maybe a distance out here, there's a point P, and the distance between the center of this object and point P, let's make it 3.35 meters. Now we know that around this charge right here, there's a mysterious, invisible electric force field. And the question is, at point P, how strong is that field? Well, the symbol for electric field strength is capital E. So what we're trying to do is calculate E at P. Now, there's two ways of going about doing it, ladies and gentlemen. The most fundamental way of figuring out the electric field strength is done by pretending to put a positive 1 coulomb charge at P and determining how much force acts on it. So the method one, pretend to place positive 1 coulomb at P. 2, calculate force on the positive 1 coulomb at P. 3, use E equals F over Q to get the electric field strength. I'm going to call this method 1. So let's take a 30-second quick 2 o'clock stretch. We're running a little late, and then we'll get right back to it. Okay, so I'm going to pretend to place a charge of 1 coulomb at point P. I'm going to call that charge Q2. Back to physics, folks. The charge that created the invisible electric field, we're going to call Q1. So I pretend to place a positive 1 coulomb charge at point P. Now, I'm going to calculate the force that acts on that charge by using Coulomb's law. F equals K Q1 times Q2 all over R squared. K is the electrostatic constant, 9 times 10 to the 9th, Newton meters squared over Coulomb squared. Q1 is going to be positive 5.8 times 10 to the negative 6 coulombs. Q2 is the positive 1 coulomb that I placed there, or pretend to place there, and the distance R is 3.35 meters.
Squared.
And then that whole bottom gets squared. Thank you. You need a little calculator help. What does that crunch out to be? Don't forget the square. What do you got, Reed?
4651.
4651. Okay. Units? Newtons. So 4,651 newtons. That's a big force because 1 coulomb is actually a big charge. Okay? Yes?
For the next step, when you find E, which Q do you use?
Good question. The Q you use is Q2, the charge that's placed at point P. Okay?
Well, here it wouldn't matter then, right? Because it's not going to change. Because it's...
True. True. So let me now step 3, I'm going to use E equals F over Q. And how much force act on that sucker? What was that number again, Reed? This is going to be Q2. 4,651. newtons. And how much force? Well, that force acted on how much charge? Well, how much charge was placed at that point? When we pretended to put 1 coulomb there. So what is the electric field strength? 4,651 newtons per coulomb. Now notice, if we did this problem all over again, and we started back, step 1, and instead of pretending to place a 1 coulomb charge, let's say we pretend to put a 2 coulomb charge right there, yes? You don't have to write this down, just see if you can follow me. And then we come over here, this here would be positive 2 coulombs, yes? So this right here would be positive 2 coulombs. So basically what would happen to this number here?
Double.
It would double. Could you double that for me, Reed? 4,651 times 2?
9,302.
What's that?
9,302.
So this is how much force would act on 2 coulombs, yes? And then we go to our step 3. And basically now this is 2 coulombs, right? But how much force act on it? 9,302 newtons.
It's the same value.
And when we calculate the electric field strength, you still get the same number. So does the electric field strength depend on how much charge you place at the particular point? No. No. Right. Does the electric field strength depend on the big papa charge that's creating the invisible electric field? Yes. Yes. So this leads us to the second method, folks. Rather than playing this game, pretend to place a 1 coulomb charge, calculate the force on the 1 coulomb charge, and then use equals F over Q2. Okay. Now that we know that, it really doesn't matter what Q2 is, let's look at the formulas. Let's look at the algebra. We know that the electric field strength at that point equals the force that would act on a charge when placed there, yes? But we also know to calculate the force on that charge, it's equal to K Q1 times Q2 over R squared. So if we substitute that in for the force, we get electric field strength equals K Q1 Q2 all over R squared, the whole shebang thing over, because that's your force,
Q2.
over Q2. And does it matter really what Q2 is? No. What happens with the Q2s? They cancel each other out, and you're left with the handy-dandy formula E equals K Q1 all over R squared. So what does the strength of the invisible, mysterious, magical electric force field around the charge? K Q1 over R squared. So it depends on 2 things. How big the charge is that created the invisible electric field, and how far away you are from that charge. You with me, people? Okay, so the last thing I wanted to talk to you about is sometimes you would have 2 charges. Say a charge here equal to, let's say, positive 5 times 10 to the negative 6 coulombs. And then maybe up here you had a charge of negative 4 0.5 times 10 to the negative 6 coulombs. Whoa. And maybe the distance between here and here is 0.35 meters. And let's say we come out perpendicularly over here to some point P, and we want to calculate how strong is the invisible electric field at point P. We would also need to know this distance here, and let's say that this distance here was 0.40 meters. Not drawing a scale. This turns out to be a little bit of a tough problem because of the vector nature of electric fields. Yes? See if you can follow me on this, people. Ready? If I put a tiny imaginary free to move positive test charge at that point P, how would that positive charge respond to just this one alone? Forgetting about this one for a moment, how would the yellow little positive test charge respond to this negative charge? Which way would it move? It would move towards it, yes? Like that, correct? I'm going to call that, whoa, let me back that up. E1. How would I calculate E1? I'd have to use the formula E1 equals K Q over R squared. And what would be the Q value for E1? If I was only considering the electric field at point P due to this guy, what would it be, Reed?
Negative 4.5.
Yes, this right here would be the negative 4.5 times 10 to the negative 6 coulombs. I actually take the absolute value because I don't really care about the negative sign. All right. To get the direction, I just pretend to place a positive test charge right there. And what the little positive test charge would do, that gives me the direction of the electric field. So I would have to use this formula to get the magnitude of that vector right there. And that would give me the strength at point P due to this one right here. But then I would have to do the whole thing over again, and I would have to pretend to place a positive test charge right here and ask how would it respond due to this charge over here? How would the positive test charge respond to this guy right here? Which way would it move now? A positive charge would move up this way, yes? Okay. And I'll call that E2. How do I get E2? Well, I'd have to use E2 equals K Q over R squared. And again, I usually use the absolute value because I don't care about the sign in this formula here. But what's going to be my Q this time? Anyone? This time I'm considering the strength of the field here due to this charge. This guy is creating an invisible electric field around it. And I'm trying to find how strong is this guy's electric field at point P. So what would I use for my charge? Dylan?
5 times 10 to the negative 6.
Exactly. Exactly. What would I use for the distance? Brianna? Exactly. You'd have to do a squared plus b squared equals c squared. Totally doable. So now you got the electric field at that point due to this guy, yes? So now you have two answers. An answer due to this guy, and you have an answer due to this guy, but these are vectors. So guess how you get the total electric field? Head to tail. Or component method. One way or another, you have to find the resultant electric field. So it's a little blast from the past with some vector stuff.